Okay, then it's time to start. I'm gonna start the presentation. Alright, hello everyone, thank you for coming today. Today I'm gonna talk about Visual Slam webinar, ORB SLAM review today. So, first of all, let me introduce myself. My name is Dongwon Shin, and you can call me just Won, W-O-N. And currently I'm working for StrataVision, which is the autonomous driving software startup, as an algorithm engineer. And before that I worked for SOS Lab, which develops the LiDAR sensor. And I got a PhD degree in computer science at GIST, as known as Gwangju Institute of Science and Technology in South Korea. And I have been the manager of SLAM2 community, Facebook community, and the YouTube channel. And lastly, I had a lot of presentations and workshops specialized in SLAM technology at various places. So if you want to know more about me, then please check the website below here. And without further ado, I'm gonna start it. Yeah. Play. Yeah. ORB SLAM is the very famous open source SLAM system among feature-based SLAM method. As you already know, as you can see in this demo video, this algorithm extracts the features from images like this, and by using them it estimates the location of the camera sensor and produces the environment map. So green dots in the image here, those are the ORB features, and black and red dots over there are map points produced by the triangulation. So you can find those kind of demo video. So again, ORB SLAM is the highly cited and renowned feature-based monocular or LGBT stereo SLAM system, having over 4,306 citations and 7.8K GitHub stars and 4.4K forks. You can check those scores on the GitHub repository. And the overall flowchart of the ORB SLAM system looks like this over here. It has the three major parts: tracking, local mapping, and loop closing here. So first of all, if you get the image frame from the image sensor over here, the tracking part is proceeded first. Then in the tracking part, the ORB feature would be extracted and map initialization is conducted. And then track local map and new keyframe decision would be proceeded. And then the tracking part is done. As a consequence of tracking part, the new keyframe would be generated over here. Then in the local mapping part, the new keyframe insertion and old keyframe calling or deletion would be conducted. And similarly, new map points are created and old map points are deleted here. And in the middle of local mapping, the local bundle adjustment would be conducted over here. And last but not least, the loop closing part would be over here. The loop closure is to determine whether the current position, current location is visited before or not. So after detecting the loop closure first, then the correct loop would be added to the graph structure. Yeah, I'm gonna explain a little bit detail later. So that's the overall flowchart of the ORB SLAM system. And so I'm gonna explain the details of each building blocks from now on. So first of all, I need to introduce the underlying data structures of ORB SLAM, right here. Map points, keyframes, co-visibility graph, and essential graph. So map points are literally the map point, main point on the map in the 3D scene. So it consists of 3D position and viewing direction, as known as normal vector, and the ORB descriptor of this map point, and the keyframe. And then the keyframes are the subset of general frames which has the distinctiveness different from the general frames. So it contains camera poses. So camera pose means it has rotation parameters and translation vector. And the camera intrinsics, it means focal length and principal points. And all the ORB features extracted in that frame. So those are ingredients in keyframes. So in this figure over here, the map points are generated by, represented by black and red dots, and keyframes are blue view frustums over here. You can see the trajectories of the camera movement. That's the keyframes. And the co-visibility graph is kind of the undirected weighted graph. So which the graph node is the keyframe, and the graph edge means the connection or association between two nodes. So if two keyframes share the same observations of the same map points, then those two keyframes would be connected each other, and they have their own weight vector, weight value. So weight means the number of common map points between them. So over here in the right part of this slide, you can see the co-visibility graph in this figure. So yellow, green edges, those are the graph edges. And the essential graph, lastly, essential graph retain all the nodes but less edges than co-visibility graph. So it has the subset of edges from the co-visibility graph with high co-visibility plus loop closure edges over here. So you can see those more sparse subset of co-visibility graph representation over here. So that's the essential graph. Yeah, those are the data structures in ORB SLAM. So back to the flowchart, I'm gonna introduce the tracking part first. As a first step of the tracking part, we need to find the initial correspondences using ORB features for tracking, mapping, and place recognition later. And ORB feature is robust to rotation and scale transformation a little bit, and has a good invariance to camera auto gain or auto exposure and illumination changes, kind of those changes. And it is fast, very fast to extract and matching, allowing for real-time operation. So it is good. It is very appropriate to the SLAM, especially SLAM for pores, not for structure from motion. So it shows a good precision and recall performance in backup visual word place recognition. So in this figure, you can see the example of ORB features. Maybe you guys already familiar with those kind of features. So you can check this image. The features are on the corner or edges or boundary areas. So those are that we are going to use for later module. Okay, so the map initialization is important module in ORB SLAM system. So it computes the relative motion between frames, two different models, which are fundamental matrix and homography matrix. So the fundamental matrix represents the relationship between two different views in the general scene, and the homography matrix here does that in case that planar structures are included in the scene. So after scoring the two models by this symmetric transfer distance measure, we're gonna select a model which one is appropriate for current scene. So if the scene is more general, then fundamental matrix would be fit for that scene, and if the scene has kind of planar structures in it, then homography matrix would be explain more well explain those relationship between two views. So then we're gonna select one of them, and we can initialize the map first, and then so after selecting the proper model for the scene, that means we know the relative transformation between two views. Then now we can make a 3D map point by triangulation using the selected model, and then refine the camera pose and the map points by the bundle adjustment. So bundle adjustment is the nonlinear optimization model. So it tried to reduce the reprojection error, which means the difference between projected point and the corresponding point in the 2D image scene. So I'm gonna explain a little bit more later. So this video shows the example of map initialization with the general scene. So first of all, they'd like to extract the ORB picture first, and then initialize the map structure by selecting the proper model, fundamental matrix or homography matrix. Then we can initialize map very well at a first place. So that's the map initialization. And the initial pose estimation would be conducted in the first case. If the tracking was successful for the last frame, then we're gonna estimate the initial pose of the current frame by using the constant velocity model over here. So if that means the tracking was successful, then we can believe the right before velocity value would be enough to estimate next position of the camera pose initially. So we're gonna use that model first, and then we can refine the camera pose by using motion only bundle adjustment over here. So we can get the correct camera pose tracking at this point. And in the second stage, in the second case, if the tracking was lost, then the tracking was failed, then we can use backup visual WOD. That means the kind of loop closure detection. First, we can convert an image, the image frame, into a representative feature vector first, and can compare this feature vector and the feature vectors in the database that we generated right now from the first to the now time. Then we can find the similar scene. That's the loop closure. So first of all, detect the loop again, then we can we can proceed to geometric verification step. That means the perspective endpoint problem. So we can determine where is the camera is located by using PMP algorithm. PMP algorithm is the given 2D and 3D correspondences in the scene, then we can estimate the correct camera pose in the scene. Then we can find even if we lost the camera tracking, we can recover where the camera pose is right now. So by using this procedure. So all those techniques are the well-known algorithm in computer vision, backup visual WOD, or perspective endpoints, or bundle adjustment, and so on and so forth. Then I'm gonna skip those, but if you want to know more in detail, let me know. You can interrupt me. And then the local map would be tracked to correspond the unmatched 3D map points and 2D ORB features. And filter the map points by several conditions here. So the commit condition number 1 would be if the map point is on outside of the image boundary, then we gonna discard it. And condition number 2, the viewing direction vector of the map here, map point, has a big difference with the viewing direction of the camera over here. Then we're gonna filter out this point. And condition number 3, the map point on the outside of the specific depth range or depth interval, then we're gonna remove it. So if the point if the point is in very far away or very close to the camera, then we're gonna remove to retain the compact map representation. So, and the survived map points are matched by ORB features, ORB descriptor for later tracking. And the last module of the tracking part, the new keyframe would be decided by specific condition over here. So condition number 1 would be the more than 20 frames must have passed from the last global relocalization here. The condition number 2 would be more than 20 frames have passed from the last keyframe insertion. Then we're gonna decide this frame, current frame as a keyframe. So condition number 1 and 2 mean the new keyframe should have enough interval or enough range from last keyframe insertion or global relocalization over here. And condition number 3, current frame tracked less than 90% of points then the reference keyframe, then we're gonna select this frame as a keyframe. So the point is this module would try to select novel view. Novel means new or distinctive scene from different from the other frame, general frame. So over here, the general frames are represented by green rectangulars, and keyframes are the subset of an very representative or distinctive frame among them. So that's it. And back to the flowchart. Next part that I'm gonna introduce in ORB SLAM is the local mapping procedure. So here, after new keyframe is determined in the last tracking part, then the keyframe would be inserted in the co-visibility graph. The co-visibility graph that I mentioned before. So they can add it to the graph structure, and the backup visual world representation would be computed for later use in relocalization. And the new map point would be created as following steps, matching 2D correspondences by ORB descriptor, and filter the first matches by epipolar geometry, and initial map point creation via triangulation over here. If we already know the camera pose between them by the fundamental matrix or homography matrix, as I mentioned before, so we can set the camera pose, and we already know where the pixel is in 2D image frame, then we can shot or send the ray to the 3D scene. Then we can find the intersection of two rays, then we can find exact 3D map points in the scene. That's the triangulation. And in order to maintain a compact reconstruction of the map, the local keyframe culling would be conducted. Culling means deletion or remover kind of those procedure, and it is called redundancy check. So that means if the keyframe whose 90% of map points would have been seen in at least other 3 keyframes, the keyframe would be deleted here. So if this keyframe is already shown in I mean, if this keyframe already have the map points already seen in the other frames, then this keyframe may be not useful, not novel. So this keyframe would be deleted. And and the map points are also needed to manage it, to retain the compact map representation. So we need to detect redundant map points and delete them. It is called association check. That means the tracking must find the point in more than the 25% of the frames in which it is predicted to be visible. So this, this thing is it represents this sentence. So in the numerator part, the number of frames the map point is visible, and the number of frames the matching is found. So the ratio between them is bigger than 25%, then we're gonna remove that map point. So that's it. And after a local map point, after local map is created to the enough size, here the local bundle adjustment would be triggered. In this case, the currently proceeded keyframe and all the keyframes connected to that frame in the co-visibility graph structure, those are refined with all the map points seen by those keyframes. And over here you can see the 5 keyframes and several map points. Then we already know the association or connection between map points and keyframes over here by tracking the features. Then we can perform the local bundle adjustment of these 5 keyframes. So it is local area. It is proceeded in the local area. Then we have another global bundle adjustment also, but it will be conducted later. And the last part of the ORB SLAM's flowchart is loop closing. So in the loop closing part, the loop candidates detection is performed here. And first, we need to compute the similarity score between the backup visual word vector here. So this means if current keyframe is the query keyframe over here, and we can make the one-dimensional vector here and query keyframe. That means the histogram vector here by using backup visual word algorithm. And in the keyframe DB, we already have the keyframes that we already had from the first stage to the current stage. Then we stacked all the keyframe and the backup visual word vector of that keyframes. Those are stored in the keyframe DB, and we can compare current backup visual word and all those previous backup visual word vector, and we can get the score, the similarity score between them. And if two keyframes are similar, then we can determine those are the loop closure. So we can detect the loop closure and discard all the keyframes whose score is lower than minimum. Then we can discard those keyframes in that sense. And after that, after determine which one is the correct loop closure, then we can compute the similarity transform between query keyframe and the retrieved keyframe, and then we can find the relative transform between two. The similarity transform between current keyframe and the loop closure candidates that I already said, and yeah, those things are something like this, and this part would be considered as a geometric verification part, and in the loop fusion step, the keyframe and map point would be corrected, and the loop edges would be inserted in the call visibility graph over here, and the keyframes and the map points would be corrected in a compact and consistent manner. So, and lastly, the essential graph optimization and global bundle adjustment would be performed, and it will be correct all those position of map points, and refine all those camera poses in the scene in one iteration. So those are the main flowchart of the ORB SLAM system. So here is the demo video on YouTube. So this is kind of the example of augmented reality case. So you can correctly track the camera pose in the scene, and you can put the virtual objects in the real floor or real objects. So here is it's kind of, that means you can put virtual character or animal on the ground, then kind of Pokemon Go. So you can make your own augmented reality application using this SLAM engine. And next demo video is the virtual reality. So virtual reality is a little bit different from augmented reality, since it is blocked with the real scene. First of all, this application, they'd like to track all the features in the image and track them and associate them, and after that the background is transferred to black screen, and transition happened into the virtual space like this. This looks like some other space they are in. So if the viewer is go to the close to the wall, then it shows the edge of the real object of the scene, and so it can alert the viewer to be careful, to make them be careful. So that's it. That's the end of my presentation, but I'd like to show the real demo and the code review after this explanation. So, okay, you guys in here, and all right. can see another screen over here, and this is connected to my Linux system. And over here I already made here on Docker Hub site, I made Docker image. You can easily learn the ORB SLAM system by using Docker image. This shows, I can send this. Oops. Here is my the URL. So here I explained how to learn the ORB SLAM system. So first of all, you may need to pull the local image on your system. If your system has already has Docker system already, then you can learn this example, I think. So first, this command, copy and paste. Then your system would like to try download the Docker image that I made before. I already have those images, so I don't need to download the image, so I can still skip it. And next, hit this command over here, docker learn command, with many different arguments. Then you can paste it in the terminal. Then you can see you are in the Docker container inside, so you can check some different directories in it, and go to the home and ORB SLAM2 path. Then you can find this already built the SLAM system in it. And lastly, you can copy this command over here and paste it. Then the ORB SLAM system will be operated like this. I already included this teddy bear dataset in that Docker container, Docker image. Then you can easily learn this, this system over here. So this is the real-time demo on my desktop. And you can find the map points, black map points and red map points over here of the teddy bear doll. And you can see the view frustum, blue view frustum over there. And this system is in real time. So on the terminal, you can see many other parameters that I set. So focal length, or principal point, or distortion coefficient, and so on and so forth. That's the video demo, real-time demo of the system. And then, then back to my screen. Back to my screen. Okay. So here's the ORB SLAM2 source code. I wrote this source code repository by VS Code program. You can easily find ORB SLAM2 by googling it, and on this GitHub repository. So over here, there is 7.8k stars they have. So I downloaded it and extract the zip file and wrote the source code over here. So I'd like to explain how they are implemented in the code. Before that, do you have any question or comment on my presentation? Or you can see my video, VS Code terminal. Oops. Again. All right, then, okay. If you don't have any question, so could you share the GitHub website? Okay, you see over here. You can Googling it. Here. And then I'm gonna start the main part of the ORB SLAM system. Just a second. All right. You need to find the main function of the entrance of the ORB SLAM system. Then by searching main and parentheses, so you can find many other main functions, but among them we can select the mono.tum.cc over here. Then we can directly go to this main function. That's the main function that I executed in the real-time demo video, real-time demo right before. So that's the entrance of the ORB SLAM system of the example. So in this main function, so over here ORB SLAM2 dot system is that SLAM system. At this point, it creates SLAM system first. It initializes all system threads and gets ready to proceed frames over here. So in that system class, you can go to the inside of the class by selecting go to definition, maybe in English. So go to definition over here, or by clicking with command button in Mac or control button with Windows. Then we can check this source code header file. But I want to know is the generator of the system function, system class. So rather than header file, I'd like to go to C++ file over here, system.cc over here, maybe SLC directory, and you can see this system cc. Then you can find many functions that already implemented, but in this case, at the top of the source code, you can see the system function. This is the generator of that class, and in this function, you can see many initialization step over here. So first of all, among them, the important thing is over here. Tracking, local mapping, loop closing. As I mentioned before, those three main parts are created over here. So I mentioned it before over here. Tracking, local mapping, loop closing threads are created over here. So tracking, local mapping, loop closing. So the created class are stored in the member function, member variables over here. Tracking system, then in this generator of tracking class, it loaded many other parameters, focal length and principal points and distortion coefficient and so on and so forth, like this, and or load ORB parameters, threshold levels, and the others, and ORB extractors are created in here, and that's the generator of the tracking class. And go back to the ORB SLAM generator creator, and the local mapping class is over here, and you can see there's not much details in the create function, generator function, but this local mapping dot learn function is the main part of the local mapping thread over here. So all those things will be explained later. And loop closing is the last thread that I mentioned. So here, loop closing dot learn function is the main thread function of the loop closing thread. So back to the Visual SLAM system, and here go to the main function, main over here. So we create the SLAM class over here, and we're gonna use it read image frame from the dataset, and track monocular function would be conducted. This is the tracking part of two consecutive image frame. So in this function over here, you can see many details in it. So from the top, the left here, grab image monocular means the grabbing the image frame from the camera or from the dataset. So click over here, then we can get the image IM, and we can convert the color image to the gray scale over here, CV by using OpenCV function, CV underbar RGB to gray function. And so we're gonna make the frame class by using this image with the timestamp and extractor, ORB extractor, or ORB vocabulary. And in this frame class over here, then we can find another the functions in it. So by using the extractor class, ORB extractor left or right, so extract ORB function is the main part of the extracting the ORB feature of the image. So as I mentioned it before, this one, the extract ORB features over here is executed by this extract ORB function over here. And then rest of them are not that important now. So we go back to the grab image monocular, and after create the frame class, frame instance, and we can call the track function over here. Then in the track function, okay, just a second. Where is the definition part of the track function? Maybe tracking. Track. Yeah, over here. Tracking.cc file in SRC folder, source folder. Then you can see this tracking.track function. In this function, you can initialize the stereo or monocular camera. Maybe this should be the map initialization procedure, or else. Okay, and the track motion model part over here. Track with motion model is the if the tracking is well done in the previous step, then we're gonna use the motion model over here, as I mentioned in the presentation. Okay, here, initial pose estimation, case number 1. If tracking was successful for the last frame, then we're gonna use constant velocity motion model over here. So here, track with motion model, we're gonna use the previous velocity to predict next initial camera pose. Then over here, with set current frame, we can set the pose of the current frame by using this equation, velocity value and the position of the last frame. So we can predict the current frame initially, and then step number 2 is the motion only bundle adjustment over here. And so here, over here, all those things are the data association part, the connect the 2D and 3D map points in the scene and image frame. And these parts are those things, and after that we can optimize the pose by using motion only bundle adjustment over here. Optimize frame pose with all matches in this case. So in this function, you can find the detail, implemented detail in the tracking.cc, I mean optimizer.cc source code. So over here, they use G2O library to optimize those nonlinear nonlinear optimization problem. So they use Liebenberg market nonlinear solver for optimizing them. So over here, and vertex means the current position of the camera frame here, P frame, and set midpoint vertices by using this later over here, this for loop. They set vertex okay, maybe over here, over there, and maybe they'd like to try learn the motion only bundle adjustment too, and optimize correct camera pose in order to refine them. So motion only means they refine camera pose only, not landmark position. So we can see all those details in this optimization function. Rest of them are subtle part of the optimization. And back to the track with motion model part, that's done with the optimization. And then over here, relocalization function is the case number 2 that I mentioned before. Over here, case number 2, if tracking is lost, then we're gonna relocalize current frame first and then learn the P and P problem second. Then on the relocalization function, you need to compute the backup visual world first. Over here, compute backup visual world. In this function, over here, MP ORB vocabulary class instance, try to transform the descriptor. All the ORB descriptors in this image frame will be used in this transform function. Then this class would like to compute the backup visual world vector over here. So in this part, all those procedures are related to backup visual world library. So backup visual world is quite well-known algorithm for loop close detection. You can easily see in the GitHub repository. Back of visual world or DVOW GitHub. Then you can find the hierarchical backup visual world library. This one is differentiated, maybe DVOW number 2. It is already included in ORB SLAM system. The ORB SLAM2 use this library as well, so you can easily find the implementation or definition of the library. And after transform all the ORB features to the backup visual world vector, then we can compare current vector to all the other backup visual world vector in the keyframe database. So by using maybe over here, they try to this function maybe return the candidate of the keyframes in the database. So the candidates would be computed. After that, in this procedure, later part is the perspective endpoint solver will be performed. Over here, PNP solver. Perspective endpoints is the estimating the transformation of the camera by 2D and 3D correspondences in the scene. So PMP solver will give you the correct position of the camera in the scene. So in the PMP solver, maybe many other things are called, and this looks like just create the PMP solver class, and by using this class, maybe later part over here in this while loop, they try to find the correct camera pose in the scene. PMP solver iterate in the iterate part. Over here in this iterate function, many lines of code are implemented, but compute camera pose function in this case, compute camera pose function will operate the PMP solver in OpenCV library. Over here, all those details are for the PMP solver, but they does not call OpenCV API at all, but all those lines of code are already included OpenCV source. You know, OpenCV, Open Computer Vision library, well-known library in computer vision field. So all those lines of code are already included in OpenCV. So maybe they copied or get some of codes from OpenCV library, and they included those things in their implementation. So, and back to the iterate part, and we can get the initial pose of the camera, and after that again we're gonna after that iterate, after that back to the origin over here, then after calling the iterate function, then you can get this transform matrix over here. Then after get this transform matrix, those are initial camera pose, so we need to refine them. So over here, optimizer pose optimization class would be called. This is same kind of bundle adjustment. So I explained right before. So they try to refine the camera pose in the scene more correctly. So that's the whole procedure in relocalization part. And back to the main part. Rest of them are quite long, so I'd like to skip some of parts in the tracking thread. So next part would be local mapping. Over here. Oops. Local. Where is the, over here, local mapping thread. We saw this local mapping learn function already. So this learn function is proceeded at a first, and then it will be learn infinitely until the ORB SLAM system is exited. So this in this while loop is infinite loop. So this is the individual thread, it will be run as an individual thread. So in this case, so as I mentioned it before in the presentation, check new keyframes and process new keyframe or map point calling or created new map points or check new keyframes and so on and so forth. All those things are included in this procedure. The details are, you can check the details in each of the function. So anyway, okay. And then I'd like to explain the important part only. Maybe, where is it? Just a second. Oops. Yeah. Create map point creation is important, I think, because in this procedure, we'd like to make a map itself by using the predicted estimated camera pose in the previous step, in the previous tracking step. So create map points over here. So in this case, first compute the fundamental matrix between two view and triangulate each match. So over here, a linear triangulation method is implemented over here. So as I mentioned in the presentation file, triangulation in local mapping, maybe here. I didn't explain the details in the triangulation, but in this case, if we already got the camera pose, two camera pose, then if we have the exact pixel position of the ORB picture, then we can send ray from the camera origin to the pixel position. Then we can get the exact intersection of the two rays. Then we can find that point is the map point. So like this, and whole procedure looks like this. This is the proceeded by singular velocity composition. So this is the well-known algorithm in linear algebra. So I can copy this part, and I'd like to compare with the code. So over here, this matrix A is this part. This is the at one row they have 4 elements. First, second, third, fourth, 1, 2, 3, 4, and if over here 1, 2, 3, 4 elements equations looks like this, and this equation is exactly same as this one. So 0.31 is P31 is P is the element in projection matrix. Projection matrix is the consists of camera intrinsic parameters and extrinsic parameters in it. But anyway, this P31 is maybe over here, this one, and V1 looks like this, and P21 is over here. So these 4 elements are stacked in a single row, and then after using singular velocity composition here, compute, after decompose these A matrix, then we can get the solution of the 3D point X over here. Maybe I need to explain a little bit more detail about this, but I have many things to explain in the later parts, so I'm gonna skip first, and I'm gonna explain it more later. So anyway, the triangulation part looks like this, and the details are over here by using single ability computation in the local mapping part. And another important thing is local bundle adjustment part. In this case, back to the learn function in the local mapping class. Here, local bundle adjustment function look like this. Local bundle adjustment is the in order to reduce the projection error in the 3D scene and 2D point. So over here, they also use G2O library over here, and set algorithm and get keyframe and fix keyframe by using vertex SE3 EXP map, exponential map over here. Then we can set the local keyframe first, and if we have a keyframe that we want to fix, then second we can fix all those vertex in G2O library and add map point vertices over here. And in the for loop in this case. And after adding the vertices in G2O library, G2O problem, and we need to set the edges. Edges means geometric constraints in the local bundle adjustment problem. So we can set the edge over here and set the vertex that we made before over here. In this case, graph node is keyframe or map point. Two kinds of vertices are in it. So anyway, set vertices and set measurements over here. OBS is observations, and observations means the 2D feature position in image frame, in that keyframe image. So over here, x, y position of the image pixel. So and then we need to set the focal length and principal point, because this is the reprojection error. So we need that. We need those parameters, and then after setting those vertices, edges, then we can optimize the G2O library optimization here. Then we can get the optimized map point and optimized camera pose. Then we need to update those optimized values to the SLAM problem. So at the end of the function, we can recover optimized data into the keyframes and points over here. So all those things are local bundle adjustment problem. So local means some limited window area, limited local area from current to the past, maybe for example 5 frames or 10 frames from the current frame. We can correct all those 10 or 5 keyframes in local area, and then we can get the consistent keyframes and map points of the scene by using this step. And lastly, after last part would be loop closing. Loop closing over here. Again, the ORB SLAM creation function. So loop closing class may be created in a new thread. Oops. So in this source code, you can see loop closing run thread function. So over here, this also infinite loop because it is a individual thread. So it runs while function in the while function and create new keyframes and detect loop and compute SIM3. That means similarity transformation that I mentioned it in the last. Over here. Loop candidates detection and compute similarity transform at that point, at that frame. And then if we get the correct transformation between query frame and the candidate frame, then we can correct the loop closure. So first, detect loop function looks like this. So in this loop closing part, the backup visual word is quite very massively contributed. And compute reference backup visual word similar to score over here. And here, first we can get the backup visual word vector of current keyframe. Then we can get this vector, and by score function, this function, maybe this scoring object and score function returns the score value of the two backup visual word vector. That means similarity between them, or similarity between two views. So we can, in order to get the correct loop closure candidate. After getting those score, then we can query the database imposing the minimum score over here. Maybe this part would be the comparing current query vector with many different histogram vector in keyframe database. So those procedure may be proceeded in this function. Detect loop candidates over here. There are many. And then after getting the candidates, go to the detect loop calling part, and compute to SIM3 is similar to perspective endpoint problem. So maybe similar over here. Just find the data association between them, between frames and 3D map points, and PMP solver is performed over here. Similarly, that I mentioned before in the tracking was failed case. So I'm gonna skip it first, and then if we get the correct similarity transform between them, we can finally correct the loop. Loop close correction looks like this. Over here. Maybe first part would be over here. Learn the graph optimization, pause graph optimization first, and then we can learn the global bundle adjustment second. So in this case, mm, mm, all right, over here, optimize essential graph function over here. All those before codes are maybe preparation for this optimizing part. So we can skip those things, and in the optimize essential graph function, you can see the many G2O library code source code, and the thing in the optimization function is every time it sets the vertices and sets the edges and sets the observations in the problem, in the nonlinear optimization problem. So all those things are similar. So yeah, set problem, vertices, set edges, set loop edges. Loop edges means the loop closure detected edges, and optimize edge and normal edges, and so on. And finally, we can optimize all those for all those problems. Then we can get the optimized pose graph of the current system, current scene. Then that's the pose graph optimization part. And the final step would be local bundle adjustment. I mean global bundle adjustment function. So global bundle adjustment is quite time-consuming procedure. So they try to make another thread because we don't get stuck in this procedure. So maybe front-end tracking part need to be learned in real time. So the local global bundle adjustment is performed in another thread. So in this case over here, global bundle adjustment is object is over here. In this case, that means all those map points or keyframes and loop edges and many other values that we need to optimize, all those things made from the beginning to current situation, we need to consider all those values in this problem, and then we optimize in a global manner. So in this case, the source code is quite long. So update all map points and keyframes. Local mapping was active during bundle adjustments. That means that there might be new keyframes not included in the global BA. Anyway, and global bundle adjustment is in this function, global bundle adjustment is proceeded over here, G2 library, and set vertices and set edges and etc. and optimize it. And after optimizing function, then we can update the optimized value into the SLAM problem. So those things are correct map points, correct key frames, and so on. So the important thing is the mutex. So there are many different thread procedures: tracking thread, local mapping thread, and loop closing thread, and even global bundle adjustment thread are performed in parallel. So we need to we need to handle all those threads to avoid the critical section problem. So those are handled by mutex object over here. So I don't know, I don't much know about the mutex and the thread, but yeah, that's the point of the ORB SLAM thread procedure. Maybe that's all those things are that I prepared, and if you have any additional question or comment, yeah, let me know. Yeah, here's the comments. If the loop closing thread also does global optimization. Loop closing thread also does. After in the loop closing thread, after getting the correct loop closure edges, then global optimization would be triggered right after that. So in the loop closing thread, the global optimization is included. Next question is, does the PMP solver comes into play when there is track loss and correct compose needs to be determined? Does the PMP solver comes into play when there is track loss I don't know what exactly you say. Does the PMP solver comes into play when there is track loss and correct compose need to be determined? PMP solver is, when does the PMP solver is? PMP solver is operated maybe over here. Over here. So if you lost the tracking, if the tracking is lost, then you need to find the where your camera is again. So they first try to find the correct backup visual word candidate, and then after that the backup visual word candidate is not the exact, does not give you the exact camera pose, just is the candidate. So in order to refine the correct camera pose, you may need to do the perspective endpoint procedure. This is the you can find the correct 3D camera pose of current scene in the current environment. And maybe another thing, this similarity transform is also similar to PMP solver. PMP solver, this is the PMP solver with similarity parameter, I mean scale parameter. So because the loop closure is especially the loop closure has, if the loop closure detected, there inevitably have the scale drift. So we need to correct the scale drift by using similarity transform calculation. So in this calculation, the PMP solver is also used. Yeah, that's it. All right, thank you very much. So, do you have any more question or comment? And this is the a part of the this Visual Slam webinar is part of my lecture series. I have a Visual Slam course over here. I have 400 pages of PPT PowerPoint file. How can I see? 이건가? Oops. Yeah. From introduction to SLAM to math basics, linear algebra, risk squares, and visual key points, and so on. And the future direction of the SLAM. Anyway, I have many other details with this lecture note. So if you want to know about detail, maybe later we can make a time for lecture series. Yeah, thank you very much. So then I'm gonna finish today's presentation. The time is 10:36. So if you have any problem or question, comment, then you can give comments on via SLAM KR community or direct message in Facebook Messenger. So thank you for coming today again. So in Korea, here is almost midnight. So good night and good afternoon. Yeah. Thank you.